Hello. Okay, I'm back. Okay, this is our third video for today, and I think we'll do some examples here, and then I'll assign you guys some homework to work on in the book. Okay, so here is one that has to do with units, and notice it says here. Hopefully, you can read that. And if not, notice it's page 257 in your book. So feel free to go ahead and look at page 257 in your book. Some of the examples will just be coming from your book, although not all of them, and you can follow along in your book if you want to. Okay? So, example 1 says f primed of t, that's capital F primed of t, is equal to little f of t, and f of t is velocity in miles per hour with t in hours, right? What are the units of that, which is the definite integral of little f of t dt from a to b, and f of b minus f of a. Notice that's a fundamental theorem of calculus, okay? And keep in mind that if we're finding the area under the distance curve, or rather, I'm sorry, if we're finding the area under the speed curve, what we're really doing is we're calculating the distance, which means we're multiplying the distance times the time, right? We're multiplying the speed times the time, which is, in terms of a graph here, hours and speed, it's going to be the speed units times the time units, whatever they are. Okay? And the units, so we look here on our little integral equation, use the red one, and then we think here, this is, remember, it's f of t times dt is what we're doing here. So we think, well, what are the units of f of t? Well, the units of f of t are, since it's velocity in miles per hour, it's miles per hour, right? So those are the units of f of t. Delta t, or dt, that's delta t, that's the infinitesimal change in time, all right? Its units are in hours, right? So its units are hours, right? So this is dt, right? So we're multiplying miles per hour times hours. Hopefully you can see, oh look, those cancel out, right? And we're given miles. And it's the same units as f of b minus f of a, because that would be the ending distance minus the beginning distance, basically. So it's still it's still units of miles, or still units of distance, which in this case would be miles. So keep in mind, when it asks what are the units of the integral, okay, you're going to multiply whatever the dx or the dt units are times whatever the little function units are. Those two together, multiplied together, canceling out if necessary, gives you the units of the integral. Okay, so I think we did that example on the earlier video, but that's how that works. Okay, now a second example. Okay, or actually let's do this one here. We're going to call it, here it is, sorry, lost my place for a minute. Okay, let's zoom out a little bit here. Pardon me while I zoom out. All right. Okay. Okay, so we're going to call this example 1.5 because I inserted this in between example 1 and example 2 in the book. But here's a situation. Let's say that f of t represents the distance traveled by a person. Okay, they are at their house at time equals 0, and their speed is given by the function f of t is equal to 3t. Estimate, or in this case, actually calculate the total distance traveled in 2 hours, because this is going to be the exact distance, just like we had before the instantaneous rate of change, right? This is, which was the derivative. This is the exact distance, which is the definite integral, okay? Okay, so distance traveled in 2 hours, and that's, in other words, after t is equal to 2, right? Well, f of t, remember, capital F of t is going to be the total distance traveled. And I made a little picture of it here, right? There's t is equal to 2. And our fundamental theorem says that the total distance traveled, okay, I'm going to write it out here, f of b minus f of a is equal to the integral of, from a to b, of little f of t dt, all right, evaluated from a to b, right? So we did this before. We used our little antiderivative formula that we said that, okay, if the derivative is equal to 3t, then the function that has 3t as its derivative has to be 3t squared over 2, because you can see if you take the derivative of this, the derivative of this would be equal to that. So if this is if this is f of t, this is f primed of t, which we've been calling little f of t. Yeah? Okay. So that's what I did here. So we said here, we took the antiderivative of 3t was 3t squared over 2, evaluated from 0 to 2. Okay, I wrote that kind of small, but the derivative of 3t squared over 2 evaluated from 0 to 2, that looks like this. We just take our antiderivative, which is 3t squared. That works out to be 6. That works out to be 0. So that exact distance traveled is equal to 6. So if you can evaluate the antiderivative, that's how that works. Now, the beauty is it don't matter what little f is. Little f can be any function you want. It doesn't have to be this simple little linear function that we already know how to get the antiderivative of. It can be cosine. It can be any function at all. That as long as we can figure out what the antiderivative is, we can evaluate the area under that curve. Okay? Now, here's a more specific example dealing with that. Okay? And that is example number 2 in your book. Okay? And that's this guy right here. And I'm going to, again, I'll just kind of white this out down here so they don't get confused. Okay, and I'm going to go ahead and I'm going to yet again zoom in so we can see that better. Okay. Right. Okay, and again, this is example 2 in your book on page 257. Okay, so this is going to sound different than the velocity and speed and distance problem we just did, but it's exactly the same situation. Well, not the same situation, but the same logical method for calculating, for getting the answer. Okay, let f of t represent a bacteria population which is 5 million at time equals 0. In other words, f of t represents the total number of bacteria. Okay? Now, after t hours, the population is growing at an instant rate of 2 to the t power million bacteria per hour. In other words, keep in mind that when we worked with population growth before, we often saw population growth as being exponential in nature. But when we worked on it, we worked with the rate at which it was changing, the rate at which the population was changing. Now, because we're working with definite integrals, we can calculate how many bacteria there are. We can talk about population totals knowing what the growth rate is. And like I just said, growth rates of populations is a pretty well-known thing. Okay? Anyway, so it turns out here that that's the growth rate, which is 2 to the t million bacteria per hour. Okay, estimate the total increase in the bacteria population during the first hour and the population at t is equal to 1. In other words, by how much? How many more bacteria came in that hour from 0 to 1 after it was already 5 million? And then what would be the total population after 1 hour, including the initial 5 million? Okay, so look at what we've got here. And I'm going to add some more here, but it says that it's growing at an instantaneous rate. Okay, so that means that little f of t is equal to 2 to the t. And remember, little f of t is equal to f primed. Okay? So we have this construction here, that the change in population from hour 0 to hour 1 is capital F of 1, the total population after 1 hour, right, minus whatever the population rate, whatever the population was at hour 0, which was actually 5 million, is given by this. Okay? From 0 to 1, 2 to the t dt. Okay, where 2 to the t is little f. Keep in mind, this is very important. Okay, when we did definite integrals, okay, when we had something like this, f of t dt, that function right there, oopsie, you can't see it, sorry. That, zoom out. Sorry, I hope your eyes are better than mine. Okay, there it is. Okay, this little f of t is the rate of change of the capital F. When we worked this problem before, we started by knowing f, and we said, oh, what's the rate of change of it? And we took the derivative. But now, we're going to be dealing with problems where we're given the rate of change. And through this integral process, we work backwards to what the original function is. Now, why would we want to do that? Well, in this case, in the case where we're given the speed, that tells us the distance traveled. In the case where we're given the rate at which the population is changing, in this case increasing, which is a very well-known thing, that'll allow us to calculate the population total. Okay, which is something that actually is, especially if you're talking about bacteria, well, they're little buggers and they're hard to count, right? So it's much easier to get the total population this way. Okay, so anyway, so this is why we've got 2 to the t. That's the rate of change of the total population, right? And so we want to do the antiderivative here. Now you're going, oh, Mr. Waters is now going to tell us. No, I'm not. Okay, this antiderivative formula we may talk about later on. Okay, it says here, and we're going to follow the book's advice, we're going to use the calculator to find to calculate the integral. Okay, now I'll do that in a minute. Okay, I'll show you exactly how to do it on the calculator here, but I don't want to break up this flow here. Let's pretend that we just used the calculator and we figured out that that was 1.44 million bacteria. So in other words, the increase from time 0 to time 1, the population gained 1.44 million bacteria. So that would look something like this. That's 2 to the t, and we just calculated the area under the curve, which is the total population, right? Okay, so that's what integrals do. They calculate totals, knowing growth rates. Okay, well, among other things, that's what they do. And there's many, many applications for that. Okay, so here, now, so that turns out to be 1.44. Okay, so we started out with 5 million, so we add the 5 million to the 1.44 million, and that gives us 6.44 million bacteria is how many we have total after 1 hour. So if you're feeling ill right now, you know why. Because the growth rate of bacteria is fast. Okay, now, how did we do that on the calculator? Okay, so keep in mind we're using the function 2 to the t, right? So I'm going to go to the calculator here, and I'm going to zoom in, And I'm going to try to zoom in close enough so that you can really see it. You know, see those? Okay, there we go, just like that. Okay, cool. Hopefully you can see that, and then also you can see part of the top of the calculator as well. Okay. Okay, so. All right, now we want a numerical integral. Okay, so I'm going to type. Now I showed you one way to before by graphing it. That's actually not the best way to do it. I'm going to find my math key. See, I'm pointing at it right here. It says math. Woo, math. Right there. Okay, math. All right, now down at the bottom, can you see it? Choice 8. It says F int parentheses. That's the integral. Now, by the way, if you've got a TI-83, an old TI-83, it's not going to be this nice. Okay? But if you've got one of the newer TI-84s with the upgraded operating system, and you've got choice or one of these jobs, you'll be able to do this. So I arrow down, I hit and I choose that, and oh look, notice we get this whole big like integral picture right on the home screen, just like that. Okay, so now I just type in the stuff that I want. We wanted, what was it, 0 to 1, so I type in 0 here, and then I'm going to up arrow to 1. Now there, of course, I want the function. We want 2 to the t. So I'm going to type 2, and then I used the 2 down here. I typed in 2. Now I'm going to use the caret key to get us the exponent. I'm going to put x instead of t, because that's what your calculator uses, don't matter. Arrow to the right again. See, I'm using the arrow keys. Arrow over to this last box, and you just type in an x. So in other words, as you can see, what we're typing in there is 2 to the x dx from 0 to 1. Now I hit enter. Boom. Ooh, 1.44. That's what we got. Okay, so that is the amount of integral. That's the area under the curve. Okay, let me arrow back up again. We just evaluated, we just measured this exact area here. Okay, so it's 1.44. So that's where they got here the 1.44 million from. That's the amount that of population was added in the first hour, and then taking into account the 5 million that you started out with, you ended up with 6.44 million bacteria at the end of the first hour. Okay? Very good. Okay, so that's how that goes. All right, now, here's another example here. Okay, 2 cars. I'm going to go ahead, let me push this up here. Okay. I'm going to zoom back in again. Not too much. Okay. 2 cars start from rest at a traffic light and accelerate for several minutes. Figure 5.32 shows their velocities as a function of time. So, which car is ahead after 1 minute and which car is ahead after 2 minutes? Well, keep in mind here that this is not a distance graph. This is a time. This is a speed graph. So this is giving the speed, and this is giving the time. So the distance, if we want to know how far ahead are they, we have to look at the area under the curve in order to evaluate that. Okay, so here is the first minute. Okay, can you see that car 1 is that distance, is that area there? In car 2, well, car 2, its distance is the red area here, you understand. That's how far it went. In car 1, it's that red plus this blue area up on top is the total distance that car 2 traveled. So you can see that car 2's up to the first hour, where at that point they're going the same speed. even though they're going the same speed, as it happens at exactly hour 1, you can see that car 2 traveled further. Okay, does that make sense? Why? How could that be? Because you can see it at points from 0 up to 1, it had a higher speed. That's why it traveled further. Okay. How about at the end of 2 minutes? Well, at the end of 2 minutes, that's interval here. So we can see, well, we don't know exactly how to measure that distance yet, but you can see that this red area, which is going to be the distance that car 2 traveled, that's this area, that big red area, is more than the blue area here, the area down here that car 1 has traveled, since we can see that visually at least this red area is bigger than the blue area. At the end of 2 minutes, car 2 has traveled. Keep saying hours, I guess it's minutes. At the end of 2 minutes, car 2 has traveled further. Again, why is that? Again, that makes sense because you can see that its speed is higher. Okay? So remember, when we're judging totals, we're looking at the area under the curve, not how high the curve is. Do you guys follow that? Now, of course, the higher the curve, the bigger the area, probably. But remember, for totals, for integrals, we're looking at the distance. Okay? Very good. Now, so here is a more sophisticated example here, and we'll spend a few minutes on this one. I think in the next video, because we're getting 20 minutes in. Okay, and you can start to look at your homework right now if you want to. Okay, I'm going to be posting the homework. You can start to look at that. Okay, because some of the problems are covered by my lessons and by the examples we've done so far. But I'm going to put this example here, which is kind of a long one. I'm going to put that on a separate video. Okay, that'll be the last one. Boom.